So what is a differential equation? So there's a definition here. It says an equation that contains an unknown function and some of its derivatives. So an unknown function, we typically use y, and it says some of its derivatives. So we could have y prime, y double prime. If you prefer, you could write, uh, triple prime. So 3. It could equal 0. It can equal functions of x. It could also equal other functions of y. So all those different things can be a differential equation. The important part is that you have at least one derivative and the initial function. So then we can start to describe differential equations. And we use terms like the order of the differential equation. The order comes from the highest derivative. So again, if we just look here at a, for instance, we only have the first derivative there, right, y prime. So that would be a first order differential equation. We can further describe them as linear or nonlinear, but for this class, the content will be just linear differential equations, so we don't have to worry about that. Now there's the thing that I think is the most interesting part of differential equations are the solutions. So we are used to a solution being something like x equals 2, or the volume is 27 pi over 12. But for a differential equation, the solution is a function. So for a down here, right, y prime plus y equals sine x, the solution we're looking for is going to be a y equals equation. And the part that I think is interesting is that these can be a family of solutions. So it doesn't have to be a clear-cut solution, right? There's a bunch of different solutions that work. And that's typically because we have plus c in there. So we would have something plus c. So that c now is what differentiates between two types of solutions. So let me just define those before I continue. So down here, I believe it was. So there are two types of solutions. There is a general solution, and there is a particular solution. The general solution contains c's, so plus c, or has a multiplier or a coefficient of c's. The particular solution, we've already solved for c. So we'll go back and talk about that again. Just wanted you to be aware that there's two different types. So our first job in differential equations is to prove a solution that's given to us works for that differential equation. And again, let me just give you a little bit of background about these solutions. So another nice thing about differential equations is if you can look at the equation, you might be able to guess a solution And if you're able to prove that that solution works, then it is a solution to the differential equation. So it's kind of nice, you can guess solutions sometimes to differential equations. Another thing about differential equation solutions is that they are what is called linear independent solutions. So by that I mean these two here would be linearly independent from that solution. And what do I mean by that? Well, linearly independent solutions basically just means there's no way to write one solution as the other. So I can't use, say, for instance, a bunch of trig identities to write those two solutions as 10e to the minus x. All right, so let's go ahead and prove that the solution given here is in fact a solution to that differential equation. Now the way to do that is to take the appropriate derivatives and substitute them all into the differential equation. So in this differential equation, we have y prime and y. We already have y here. I just need to find y prime. So how do I do that? Well, I just take the derivative. So what is y prime here? Well, derivative of sine is cosine. Derivative of cosine is minus the sine, and it's already minus, so this becomes plus. And the derivative of 10e to the minus x is minus 10e to the minus x. So now I need to take y prime, plug it in there, take y, plug it in there, and prove that what comes out of the left-hand side is equal to sine of x. So this is kind of reminiscent of trig, when you would prove the trig identities, right? You take the left-hand side and prove that you get the right-hand side. So if I plug in y prime first, now y, and we're trying to prove that it all comes out to that. So I see that I've got a half cosine minus a half cosine. They cancel. And I've got 10e to the minus x and minus 10e to the minus x. They cancel. So 1/2 sine plus 1/2 sine is a total of sine. So you would say something like therefore, I don't know if you've seen this symbol before, 3 dots in a triangle means therefore y is a solution
So is this a general or a particular solution?
This one would be particular because there is no plus c.
Gotcha. Thank you.
So you can either have plus c, or you could have something like c1 natural log x, something like that. But if there are no c's, then that means that it should be a particular solution. And if we had much more time to cover the topic, right, we would learn that the family of solutions, right, you get this plot, and it's called a vector field. So you get all these, curves that look something like this, right? Let's say. And so all of these would be a solution to a differential equation. And when you solve for that c, right, those coefficients or constants, that means that they pass through a particular point. So that's why it would be general when you have a plus c or multiplied by c, because it could be any of these curves. But if you want it to pass to a particular point, that would be a particular solution. I think I will leave this one for you. And I guess I'll leave this one. All right, so C. So this one is what kind of solution?
General.
That's a general solution. What about the differential equation? Is it, what order is this differential equation?
Second.
Right, second order, because it's the second derivative is the highest derivative. Our test to prove that this is in fact a solution. So because it's second order, we need y prime first. So the first derivative of this function is going to be 3c1 e to the 3x plus, actually negative, right? Because there's a minus 4 c2 e to the minus 4x. Now, you could in fact throw this 3 inside the c1, but you'd have to call it something else. And because we're trying to eliminate everything, that's a bad choice. So that's why I chose to do this one. So it was clear that you leave the constants alone. Y double prime. We bring another 3 down. And here we bring down another negative 4. And that's what we should get for y double prime. So now we need to plug y double prime, and y all into that equation and prove that it equals 0. So y prime okay. Then we need, it says y double prime, then we need y prime. And then finally we have minus 12 times y. And we want all that to be 0. So if we look, we've got c1 e to the 3x, c1 e to the 3x, and c1 e to the 3x. So we have 9 plus 3 minus 12. And then we also have a c2 e to the minus 4x term. And it's multiplied by 16 minus 4 minus 12. So both of those coefficients, right, 9 plus 3 minus 12, that goes to 0. And 16 minus 4 minus 12, also 0. Now, I think off the top of my head, I want to say all of these turn out to be solutions, but just keep in mind that that doesn't always have to be the case. So I'll leave those other two for you. I'll talk about these solutions again, and then I'll start separable, and then I'll break you guys out and let you try some of these problems. So again, we were talking that there's two types of solutions, the general and particular. So notice here in this example, it says for this differential equation, y double prime plus 16y equals 0. One of the solutions is 2 cosine 4x. But it turns out that 3 cosine 4x works, and so does 4 cosine 4x. So it looks like it doesn't matter what the coefficient is, it's still a solution to the differential equation. Therefore, we could say that the general solution is just some coefficient, C1, times cosine 4x. And that's our family of solutions. Now, if we want one that passes through a particular point, say x1, y1, that is called our initial condition, right? Instead of C there, it could just say y1. So that's an initial condition, or sometimes you'll hear me say initial value because it's called an initial value problem. And if you use that to solve for C1, that is then called a particular solution. So I think we'll get a chance to do that in this next section. So this first problem here, this right here is our initial value. So any questions so far? All right. So another neat thing about differential equations is it's really the first time that you get to use integration and differentiation at the same time and apply it to problems. So the first kind that we're going to talk about is called a separable differential equation. Now that has to start out in this form. Well, at least for us to solve. So let me just motivate the separable differential equation before I solve that. So let's say I've got some function, call it big F, that is both a function of x and y. So it could be something like x squared y, for instance. Now, in order for it to be a separable differential equation, well, then I need, for instance, f of x, y to equal, say, dy dx. And I need to be able to separate my function big F here into two functions, a function of x and a function of y. So hopefully it is clear to you that if I started with something like x squared y, it'd be very easy to separate that into a function of x and a function of y. All right, x squared could be my little f of x, and this could be my g of y. Now, if I can write the function that way, then I can take f of x, g of x, and separate my differential equation, right? So I got dy dx. I can take the dx to this side and take my g of y to this side. Now, granted, they write the function times g of y, but typically it would be f of x dx equals dy over g of y. And it just looks better if you write it this way. So instead of calling it g of y, we could have called it something else, and then we could write it as a multiplication. The point being, one side of the equation has all x, the other side of the equation has all y. That is the reason for calling it separable. So my only task is to get all of the y's on one side, all the x's on the other. Once I've done that, notice I have a differential on both sides, right? I have dx on one side, I've got dy on the other. You can integrate at that point, both sides. So notice up here in the steps, it says, get it in the form where it's all x on one side, all y on the other. Integrate both sides. Solve for y if possible. We'll get into that. And if the problem is an initial value problem, it should say, solve for the constant of integration. So I'm going to guess that half of you are sitting there going, I have no clue what's going on. This all looks like gibberish. So let me go ahead and do a problem and see if everything I just said starts to make some sense. And feel free to stop me if you have a question. So again, I'm trying to get all x on one side, all y on the other. In this problem, it's real easy because I can just cross multiply. So y dy is equal to x plus 1 squared dx. Everybody agree with that?
Yeah.
Okay. So that was very easy to get it from the initial differential equation, and now it's separable, right? Because it's got all y's on one side, all x on the other. So at that point, we can integrate both sides. Integral of y is great. It's just y squared over 2. As a technicality, I'm going to put plus c1 just for the first time I do this. On this side, I'm going to have, I could do a u substitution if you like. So this is really the integral of u squared du, which would be u cubed over 3. And plug in u, which is x plus 1. Now on this side, I get another constant, right? Because anytime I have an improper integral, sorry, not improper, can't think of the term off the top of my head right now for some reason, an integral without bounds, then we get a constant of integration. However, if I were to simply move this C1 to the other side, I can add it to that C2 and it would just become C. So my suggestion from here on out is when doing these problems, just go ahead and put the C, the constant of integration, on the side with the X. So I've got y squared over 2 equals x plus 1 cubed over 3 plus c. Now, the problem does say,
I'm sorry, real quick. Can you go back over what you were just saying with the constant? Like, I'm kind of lost about what you were saying with just put it on the one side.
so each integral would technically get a constant of integration, right? You get a c1 on one side, c2 on the other. But if I
Right.
move c1 to the other side, then it would just be minus c1 over there, and two constants added or subtracted is just a new constant.
Right. Okay. All right, that makes sense. Sorry.
Sorry, I told you guys to stop me if you had a question, so you're fine. So it does say solve for y if possible. Very easy to solve for y here. However, we are given an initial value, and the whole point of the initial value is to solve for c. If I were to start solving this for y, I would be putting c inside of a bunch of stuff, in this case, under a radical, which I would then have to undo to solve for c. So my best advice is to go ahead and get c first, plug it in, and then solve for y. So the initial condition says when y is 3, then x is 2. Okay, so we've got, looks like 9/2. Then up here, we're going to have 3 cubed over 3, which is going to be 3 squared, or 9. So c equals 9/2 minus 9. Which is minus 9/2. So I would come back up here. Substitute that in. Okay, so this was a general solution, not solved for y. And I'm going to take this next part here and solve it for y. And that'll be my particular solution. So to solve this thing for y, I need to multiply through by 2. And then take the square root of both sides. So is anybody super lost? Are we okay? Just need to see another one.
Yeah, I'm good. I just want to see another one.
Just see what other types we had here. So we got quite a bit. I remember these bounds didn't work out for some of these. For these conditions. So I'm going to need to change them. I think this one was backwards. I think this should be that. Unless I change, we'll see. This one's not terrible. So I'll leave that one for you. That one's not terrible either. Let's go ahead and do this one together. And then we'll see about it. I'll probably do one more. So let's forget about this condition for now. I'm going to give a condition at some point, but what I remember, this one getting plugged in doesn't work nicely. So I don't want to use it. So let's go to the equation here. So this is first order. I see the first derivative is the highest derivative given. Now, because it's separable, the best choice is probably to immediately write that this way. Because we know we got to get all the y's on one side, all the x's on the other. So I am going to, just to prove a point, I'm going to move this x to this side. And I'm going to move this dy to that side. So to move the x to the left, I would need to divide by x. And same thing with the dy. To move it to the right, I would need to divide. Now I did that on purpose because notice my differentials are in the denominator. Have you ever seen an integral like this before?
No.
So anytime you have an integral, the differential has to be in the numerator. So what did I do here? Is there a way to fix it?
Instead of dividing by dy, would you divide the other side by dx?
So I could multiply dx to the other side and divide by y, right? I could have done that. But I did it this way just to prove a point. Is there a way to fix it now that I'm here? So you're correct, but I'm asking, is there a way to fix it now that I'm at this point?
I want to say something with multiplying it,
Take the
but I
reciprocal.
don't know.
So yeah, I was gonna say, you know, this is true, right? And so is
Yes.
this.
Yes.
So if I have fractions and I flip both of them, they're still equivalent. So I can just flip both of these over. So I just did this because I see people do it a lot. And they just throw the integrals in there and try to do it. But I want you to realize that you can't have your differentials in the denominator. And if you do, and they're fractions, just flip the darn things over and you're fine. And then, do we know what is 1 over cosecant equal to?
Sine.
Are you sure? That sounded like a question.
No, I'm sure.
Okay.
My brain's like moving slow today. Sorry.
That's every day for me. Don't worry about
I thought you were gonna say it was every day for me.
it. So if we change the cosecant into sine, we can integrate both sides. What's the left-hand side?
Natural log absolute value of y.
Okay. And then the right-hand side, we got to do by parts.
Negative x cosine x.
So we have that, right? So we have natural log y equals all this. Now we do not have a condition yet. We had the one that was given before and it was ugly. Let's see. Let's say y of pi over 2 is equal to e squared. Let's try that. So if that's our initial value, then we would plug in, this would be natural log of e squared. And over here we would have minus pi over 2 cosine pi over 2 plus sine pi over 2 plus c. Right, I just substitute e squared in for y and pi over 2 for x. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. The log of e squared, right? E squared is obviously positive, so we don't need the absolute. Natural log of e squared is just going to be 2. Because natural log and e are inverse functions. So you get c equals 2 out of that. So then we have natural log of y is equal to this. And then solve for y. So I'm going to take e of both sides.
Wait, why is C2? Shouldn't it be 1?
Oh yeah, I forgot to move this 1 over, didn't I? Silly me. Thank you. There we go. All right. And then I took e of both sides here. These are gone. Solve for y. I'm going to write this exp. That's just another way to express e, because I want it to be clear that all of this stuff is inside the exponential. So natural log of y equals this was the general solution. This is the particular. You have a question?
No, no.
All right, let me see what other one. So I'll change this one as well when I give it to you.
Professor,
Yeah, go ahead.
would you mind scrolling back up for just a moment?
I suppose.
Thank you.
Is that good?
Yep. I'm all set. Thank you.
So I'll do one more for you, and then I'm going to set you guys loose and let you try some. Let's see. I'm going to do this one or this one. Or that one. Any of them in particular you guys would rather me do? Out of the three that are left?
C.
All right, so let's take a look at that one. So we've already got x dx on the left. So if I just divide by the radical, that'll get us all y on the right. So once we've done that, this is separated. We can integrate both sides. So the integral of x dx, that's lovely. That's just x squared over 2. What about this dy over the square root of 1 minus y squared? Does that look familiar?
Is this one of those like trig substitutions?
We could solve with a trig sub, but do you recognize this one already?
Is it inverse sine?
I think it's inverse sine. Check and make sure. Or we could do it really quick. We could say y is 1 sine, dy is cosine d theta. That's cosine theta d theta over 1 minus sine squared. 1 minus sine squared is cosine squared. Square root of cosine squared is cosine. So you end up with integral d theta, which is theta. Use this to solve for theta. So yeah, inverse sine. So yes, it is a trig sub, but it's super easy. Takes 2 seconds to do it. So x squared over 2 is equal to arc sine plus c. We need to find c. So if x is the, well, let's see if I fixed this or screwed it up. Let's see. Yeah, this is good. Okay. So if x is square root of 2, square root of 2 squared over 2 has to equal inverse sine square root of 2 over 2 plus c. So square root of 2 squared is 2, 2 over 2 is 1. What is the inverse sine of square root of 2 over 2? Looks like pi over 4. So then just plug it back in. Oops, I put x here. No, I didn't. It's y. So I'm just going to move everything to the other side of the equation. And then to get y by itself, you would just take sine of both sides. Again, sine and inverse sine are inverse functions. So if you take sine of the inverse sine, they cancel. Why'd that move? I see a lot of students don't seem familiar with that either. Assume that's because they did not take trig and skipped and took pre-calc or something. What's that?
Can you just scroll up real quick where you wrote the sign, inverse sign at the top, just so I can see what it was?
Did you say, could I go over it again? Sorry, you're kind of low.
I just want you to scroll up for a second.
Oh, sorry.
Yeah, right there. Okay, cool.
So again, I don't think that these are, too terribly difficult. They are taking quite a bit of knowledge, right? We've got to know derivatives, we've got to know integrals, got to know our trig, algebra, all kinds of stuff. But the separation part of the problem, not very bad. And those themselves aren't typically too bad. Now, of course, as you go along, they'll get worse, but to learn the concept, they're not so bad. So let me go ahead and package these other problems together. No. You can do it, computer. I have faith. Okay, so these first two are prove the solution. These two are solve the separable so diff EQ is shorthand for differential equation, by the way. And let's see, this condition, I think what would work well off the top of my head. Maybe let's try 1/2 in there, and then instead of this E business, let's just do a number like 3, see what happens. Oops, I guess I didn't save it. I'll tell you what, when you guys get to that problem, I will I'll see your solution, and then I can make a decent choice for that. Just go ahead and copy these down. Let me know when you guys are ready, so I can stop the share and break into your groups. We good to go?
Yep, I'm good over here.
Well, I would hope that if you didn't have them copied down, you'd let me know. Go ahead and stop sharing. I'll go ahead and pause.